Hey, good morning, folks, or whatever time it is you're watching this. Welcome to my little video on power. Um, Joseph's with us. We are just doing a little bit of milk. Maybe he'll allow me to put him down before we get started. We'll see. He might stay here. We'll try it. So you might have seen power already at GCSE level. It's essentially how much energy an object can use in a certain time frame. So one formula that you can use for power is energy expended over time. Energy expended in this case you can express as work done. So there's going to be lots of like moving objects. So it could be like the work done by a vehicle as it drives along somewhere, but it can apply to like, I don't know, someone running. It could apply to like an electrical object using a certain amount of energy. Yeah, loads of stuff. The unit for power, scroll it down a little bit. It's tricky with a baby on my lap, guys. The unit for power is watt. So we're generally going to use the watt. That makes things a lot easier. But you can break down the SI units, sort of like get a bit more of a fundamental definition. So we take the formula for work done. It's a force times a distance, and time is just t measured in seconds. Distance is obviously measured in meters, and time is measured in seconds. Force is measured in newtons, but it's not a fundamental unit, so we're going to break it down, and we're going to use the formula F equals ma. And we can get a formula for that bit. So if I just write that, m times a t over e. So the unit for mass is kilograms. The unit for acceleration is meters per second squared. The unit for distance is meters. And the unit for time is seconds. So putting all that together in terms of the units, we're going to have kilograms, meters squared over seconds cubed. Whoa. So, you know, it's easier to use the watt, right? Rather than writing that beast all the time. Something like that there. We'll stick with the watt. In terms of another formula for power, if we go back to that idea of power is work done over time, we'll start there. And work done is a force times a distance, and we're dividing by a time. But looking at this formula, we could say, oh, we've got a distance and a time. We're dividing distance and time there. Therefore, I should say displacement rather than distance, but it's fine. We've got a velocity here. And that is the second formula for power. Also a force times by a velocity. Amazing. When we say force, there is a bit of a caveat, there's a bit of a catch. And that is, sorry, I dropped this milk. It's all going bad. Yeah, the caveat is there's going to be lots of forces. When you're looking at like forces in vehicles, they might be going up a slope, there might be a driving force. The force that we're talking about here is the applied force. So if it's a car, it'll be the driving force, the force applied by the engine. If it's someone jogging, it's their exertion, it's their exerted force, right? It's not going to be the resultant force or any resistive forces or anything like that. Hopefully that seems okay. Let's have a look at this example down here. We've got a car, and the mass of the car is 1,000 kilograms. Lovely. And it can produce a maximum power of 45 kilowatts. So obviously that prefix killer, we're going to multiply the value by 1,000. Can produce 45,000 watts, this vehicle. Ignoring air resistance, find the maximum acceleration of the car when it's traveling at various speeds. So I'm looking at these values, and initially I'm thinking like, what formula am I going to use for power here? Because there's two. Noticing that these are velocities, it probably seems a good idea to start with this formula, force times velocity. So that's what we're going to do. So I'm going to write the maximum power available to me over here. I'm going to take the force and I'm going to take the velocity, 12, and I'm going to rearrange this formula. 45,000 over 12. Let's see what that is. It's going to be about, yeah, there we go. 3,750 newtons. That's not what the question asks me to do, though. It says to find a maximum acceleration. So this is the driving force that the car can put out. The car can exert 3,750 newtons. And I don't have to worry about any other forces, which makes things a bit easier. So now, trying to get an acceleration, I know the forces involved. I know the mass of the vehicle. I can use F equals ma to tie this all together. So next, I'm going to do F equals ma. I know the driving force. I know the mass. And I know acceleration, and I can rearrange to get the acceleration there, 3.75. Okay, right, I think we're in the clear. The baby is down in his pot over here. I think I'm good to go. It should be a little bit easier for me to write. I've got a gummy snake. Let's do part two. And part two is going to be very similar. We're just going to have a higher velocity. We'll start by setting it up in the exact same way. I'm expecting the acceleration to be lower here. So if you're traveling at a faster speed to start with, it takes the car sort of a little bit longer to speed up, just intuitively, you know. 0 to 10 is a lot easier than 70 to 80 in a car. So hopefully we'll see that principle in action here. Power, 45,000. Force, don't know yet. Velocity, 28. A bit of rearrangement to get the force. 45,000 divided by 28. Okay, yeah, I was going to say it doesn't look like a nice number there. So that is the driving force of the vehicle. And if I use F equals ma once again, and use the mass of the vehicle, we are going to get 1.607, so on, meters per second for the acceleration there. Cool. Here's another example. This time we're going to be dealing with some additional forces. So let's have a quick read. There's another car. It's a lighter car, this time 900 kilos. Little. Well, that's not cute, but it's fine. So we've got that car. There will be a driving force. Well, I'm going to call that driving force D. And there is a resistive force. So there's 1,700 newtons worth of resistive forces. A car produces power 45 kilowatts again. That is once again a power of 45,000. What is its speed? It's moving at a constant speed. So in this question, we're going to kind of do it in reverse. A constant speed tells us that the acceleration of the vehicle is 0. It's not speeding up nor slowing down. So I can infer from that that the forces must be balanced. So the driving force, the one force going forward is going to be equal to the one force acting in the opposite direction, which is brilliant. So what I can do from there is I can use the power formula. And keeping in mind that the force that we use here is the driving force of the vehicle, so that's going to be the 1700. Power is 1700 times the velocity. Oh, I know the power. It's 45,000. So a little bit of rearranging once again, and a divide by 1700 this time. And I get a velocity of 26.47. Cool. Oh, something else here. A hill suddenly. New diagram, I guess. I'm gonna tidy this up. I'm gonna do it properly. This is a very steep 2 degrees, just for the sake of seeing what's going on here. So we've got the car, slope of 2 degrees. It's driving down the slope. I believe, yeah, downhill stretch. It still has resistive forces, newtons, but now a component of the weight of the car is acting in our favor. It's helping us go down the slope. You might remember from doing the slope work last time, the component of the weight is W times sine theta. So we've got that extra force helping us out. So what that should mean, sorry, I'm trying to rearrange, get to the lines here, is that we don't need as much driving force. We can sort of ease off a little bit if we wanted to. Let's see. So it comes to a downhill stretch, 2 degrees to the horizontal. What is its maximum speed? The power and resistance remain unchanged. Okay. So again, maximum speed, there is an implication that you can't get faster, and we're not going to slow down because we're going as fast as we can. So maximum speed implies that the acceleration is 0 and that the forces are balanced once again. However, this time there's more forces involved, right? So we've got the driving force and the weight component acting down the slope, and we've got the 1700 newtons over on the other side of the equation. Where's it gone? I'll come back. All right. So the weight of the vehicle is 900 times gravity, 9.8. I'll work out what sine of 2 is in just a second. We'll get a number for this this term. So it's going to be 9.8 times sine of 2 degrees. Am I in degrees? Oh, I could be bad. I'm in radians. 100 degrees. Okay. 307.8. Rearrange, and should be able to get value for the force here. That is going to be just under 1400 newtons. I'll move him now. I'll cut this bit out. He is, yeah. Okay, that is my driving force. Let's make a bit more space. Stuck it over there. Now that I've got the driving force, what do I need to do? Find the max speed. Okay, so I'm trying to find the velocity. I know the driving force, and I know the maximum power, so I can use the formula. Power is driving force times velocity. The driving force is 45,000. More space. The driving force, power is 45,000 The force is driving force 1392.2, and the velocity is to be found. Go. Let's go 1 decimal place. My velocity there. Cool. Amazing. So from there, guys, what I'd like you to do is to work through this exercise. There's quite a few questions, as you can see. I have got some answers somewhere. Let me see if I can find them. I think they're from last year. AS Further Maths. Aha. Yes. This exists. So what I'll do, I'll make this a PDF and you'll be able to see my answers and my fantastic diagrams and anything else that you need to help you solve the questions. Hopefully that looks okay. I'll see you all soon. Looking forward to seeing you all next week. Take care, guys.